Hey everyone, Patrick Kennedy here with Microchip. Today I'm going to show you how to improve sensor resolution using differential input ADCs. I'm going to use Atmel Studio, which I have open here, along with the START extension to program the AVR-DA variant of the Curiosity Nano development platform. Although the same method should be easily portable to any device with differential input functionality. I've also left links to resources in the video description below that I'll refer to throughout the video, such as datasheets, links to the hardware and software tools used here, and a couple of application notes. I covered the concepts and theory of differential ADCs relative to single-ended ADCs in the last video, which you can find linked below along with other items I will refer to throughout this video, like the hardware and software tools used, datasheets, app notes, and code examples. For those of you who've missed it, typical single-ended ADCs convert an incoming voltage signal to a digital number relative to ground. But what happens when the signal of interest deviates from ground? Well, it turns out single-ended ADCs cannot account for this issue on their own. Moreover, this turns into an expensive and frustrating problem when designing sensor interfaces that, either by design or from environmental factors, output these types of signals. Well, differential ADCs fix this by measuring the difference of two inputs relative to a voltage reference. This means we can tune the ADC to specific ranges of voltage inputs. It also means various types of noise will be removed, but that topic is covered more in the background video, which I encourage you to check out if you're curious to learn more. Okay, so as an example here, I have a voltage source outputting roughly 2 to 3 volts. Notice I said roughly. We can see the 12-bit differential ADC on the AVR-DA maintains its 12 bits of resolution despite this offset from ground. Now if we hook this up to a single-ended ADC, you'd see that even though the ADC I'm using here is rated at 12 bits, the effective resolution would really only be around 10 bits, which equates to around a third of the number of distinct values that we originally had. Right, so how do we actually set this up? Okay, so starting off, go ahead and open Atmel Studio, like I have here, and create a new project within the START extension with your chosen device under File, New Project from START. If you don't have Atmel Studio, I left a link in the description where you can download it. The START plugin can easily be added under Tools, Extensions, and within this window. As I said before, I'm using the AVR-DA family variant of the Curiosity Nano platform, so I'll create a new project with that device. Once the project is open, click on the Add Software Components button to add the ADC, the USART, the DAC, and the VREF drivers. The VREF module is going to provide the voltage references needed for the ADC and the DAC, while the USART is just going to print the ADC results over the terminal. Okay, so we need to make some configuration changes to the driver, starting with the USART. Click on the USART bubble to open up the configuration screen. The default settings here should suffice, but let's make sure to enable printf support and double check that the baud rate is our typical 9600. Okay, so we also need to connect the transmit and receive signals to the pins that correspond to the onboard USB CDC bridge. To find those, we can just pop open the hardware user guide from the kit window or just by searching in the browser. In the appendix section, we can find a simplified pinout, which I personally prefer for this case over the detailed schematic that you just saw me go by. But here we can see the CDC bridge is tied to pins RC1 and RC0 of the AVR-DA. So let's set those pins on the USART configuration screen. Okay, navigating over to the VREF module, we can enable the voltage reference for the ADC and the DAC, which we will then set to the external VREF-A pin and to an internal 2.5 volts, respectively. Okay, so moving on to the DAC, I'll just check this box to enable the output voltage on the pin so I can make sure the voltage reference is correct. And scrolling down, it looks like I also need to enable the DAC officially here. I'll also enable the output buffer here, which basically provides more stability in the DAC output. It's not really necessary for this case, but I like having it enabled by default. The output voltage is determined by this data register, which I'm going to leave empty for now since I just plan on loading the value within my code. Alright, so next up, the ADC needs to be in 12-bit mode with the differential mode configuration selected and the differential mode conversion enabled. The negative input, or mux-neg, as shown here, is going to be our DAC, while the positive input is just going to be the ADC input pin 0. Which we'll need to enable as a component signal coming from pin D0 by checking this box. Okay, last but not least, we need to figure out what pin this VREF-A corresponds to and make sure that that pin is configured correctly. This information is probably in the datasheet, so open that up from the kit window. Control Find VREF-A brings us to the I/O multiplexing section of the datasheet where we can see where pin RD7 serves this special function as the voltage reference for the ADC. Okay, so going back to start, open the PinMux configurator on the left-hand side panel. Find the PD7 pad and configure it as an advanced pin and set it to input. Go ahead and hit Generate Project, name your new project, and open up the onion.c file when your solution is generated. You'll notice your project was populated with a bunch of files. These are just basically APIs for you to use in your application layer as well as some initialization code. Okay, so first things first is adding some libraries that will allow us to use printf and delay functions to slow down how much information we are spitting out to the terminal. I'll also need to set the DAC output at some point, and I just want to print out the differential conversion, which I will also need to grab. And then finally, we'll just add this little delay, which is completely optional. Okay, so I need to go see what APIs I'm working with, which I'm assuming are in this DAC basic C file. Okay, so scrolling down, we can see some basic commands. Okay, here we go. This looks promising. Okay, so this sets the voltage output of the DAC based on whatever value we pass to this function. Now, from the datasheet, we know that this is a 10-bit DAC, and since our voltage reference is 2.5 volts, we should be able to just set this to 1023 in decimal to get that 2.5 volts, since that is the maximum voltage that will be output on this DAC. Okay, heading over to the ADC C file, we can find something similar. Scrolling down again. Okay, here, this looks also pretty promising. So this function returns a new differential conversion when called, given the positive and negative channel input. So we can right-click to see what that implementation looks like. Okay. So these are the macros for those channels, which means we can just call them directly from the application layer. Okay, so going back to the function, we can just plug them in with some help from autocomplete or using spacebar click. And that's pretty much it. Based on the software configuration, this is the hardware setup with the voltage reference on pin RD7 and positive input on pin RD0. So go ahead and program the device and open up a terminal emulator. I use Data Visualizer. And there we go. So there you have it. We just improved the resolution of our ADC reading with some simple configurations of the ADC. Again, check out the code examples and literature linked in the description below if you want to see the internals of how this works, test out the tools for yourself, or view some of the more advanced features like automated filtering and accumulation that are available on this device. As always, please like and subscribe if you found this video useful, and leave your thoughts in the comments below.